Hello everyone, welcome to my video on solving definite integrals by interpreting in terms of areas. So up until now, all we know is how to integrate definite integrals which have polynomials of degree 3 or less, because we have summation formulas for I cubed, I squared, I, and for constants, right? But we don't have summation formulas for, let's say, square roots. So we don't know how to integrate square roots. We don't know how to integrate, let's say, sine or cos of I, or exponential functions or logarithmic functions. We're not able to do that because we don't have the summation formulas in order to integrate them, so we'll end up getting stuck. But let's go ahead and look at functions which we actually could integrate, even though we don't have their summation formulas, but by interpreting them in terms of areas. So in this next example over here, it says to evaluate in terms of area. Do not integrate, do not anti-differentiate. So let's go ahead and solve this. This is one example where we could actually use our summation formulas. It actually works. But let's go ahead and solve it geometrically. So we begin by sketching the function. So we're taking the integral from 2 to 4 of the function 5 with respect to x. By sketching a function, what do we have? This is the y, this is the x-axis. We're going from 2 to 4. So let's say this is 2, this is 4. It's not drawn to scale. And the function's constant at 5. So at 5, let me draw it in red. We have a constant function on the interval from 2 to 4. So now we could see what shape we're dealing with here. How do we find the area of this shape? Well, without integrating, this is just the area of a rectangle. And we know the area of a rectangle is equal to length times width. What's the length and what's the width? Well, to find, let's start off with, we'll call it the width. All you're doing is subtracting 4 from 2. So 4 minus 2, gives us a distance of 2. And what's the length? Let's consider this to be the length. How high is it? Well, it's just constant at 5. So this is a height of 5. So the area of this rectangle is simply just 2 times 5, giving us 10 units squared. So this is an easy example where we could look at the function and look at its shape geometrically, and we're able to find the area under the curve, okay, giving us an answer of 10 units squared. Okay, so that's our first example. Let's look at a harder example. So here the example we have, example 2, is to evaluate in terms of areas. Again, do not integrate, do not use the limit definition to solve this, although we can. Let's find the answer in terms of areas. So we have the function 3 minus x. One way of doing this is you could separate and do each term individually. Another way is to just sketch the function over here. So the function we're dealing with is 3 minus x, and it's on the interval from 0 to 4. So let's go ahead and sketch that. This is the x-axis, y-axis. We're starting at 0, and we're going to 4. And again, this is not drawn to scale. 3 minus x. So when x is 0, y is 3. Let's put our scale here. 3, 2, 1, and this is negative 1. So if we substitute x with 0, we get 3. That's our first point. So when x is 0, y is 3. If we plug in x as 1, we get 3 minus 1, which is 2. So when x is 1, let's put our scale here too. 1, 3, not drawn to scale. When x is 1, y is 2. When we put in 2, 3 minus 2 is 1, so 2, y is 1. When we plug in 3, we get 3. And when we plug in 4, we get 3 minus 4, which is negative 1. Something like this. Okay, so we get a straight line. Again, it's not drawn to scale, so it doesn't look straight, but this is what we're dealing with. So the shape or the area under the curve that we're dealing with separates into 2 sections. We have our first area, which is here, area 1. So this region here. And then we have this small triangle here in the negative region. This we'll call area 2. So let's go ahead and find the area for this. So if we focus on area 1, we're dealing with a triangle. And we know that the area of a triangle is base times height divided by 2. So the base is from 0 to 3 because we're focusing just on this one here. So the base is 3. The height is also 3. And we're dividing by 2, giving us 9 on 2 units squared. So that's the area for this region here. And the fact that it's positive makes sense. We expect it to be positive because it's above the x-axis. Here, if we look at area 2, again, we're dealing with a triangle. So we're doing base times height divided by 2. The base of the triangle is a distance of 1. The height, depends how you think of it. If you know it's in the negative region, you could put a negative sign right away. Like, I know my answer is going to be negative. Or you could think of the height as -1, a height of -1. So it really depends on how you interpret it. What I do is I know this area here, this region here is beneath the x-axis. So I know my area is going to be a negative answer, so I'm going to just consider the positive distances. So the base of the triangle here is 1, the height of this triangle is 1, and it's base times height divided by 2. So it's going to be -1 divided by 2, which gives us -1/2 units squared. Okay. And now the final answer, we want A total. The total area is equal to A1 plus A2. Or if you want, you could have done A1 minus A2 and keep A2 to be negative. And that gives us 9/2, so it depends how you think of it, minus 1/2. Okay. This gives us 8/2, which is a final answer of 4 units squared. So the area under the curve, the net area, is 4 units squared. And we're done. So here we are solving the integral without integrating. We're considering the function and finding the area under the curve by interpreting them in terms of area. Okay, so let's look at a harder example. So our next example over here, it says to evaluate in terms of areas, do not integrate again. So we have the integral from 0 to 3, and now we're given a new function. So we have the absolute value function of x minus 2, and we're integrating with respect to x. So how do we deal with the absolute value function? So there's 2 different ways of doing this. You could actually just sketch the function as is, or you could use the definition of an absolute value function. So you could split it into the positive section and negative section. Really up to you. I'm just going to go ahead and sketch the function as is. So let's go ahead, do this. X-axis, y-axis, this is 0. We're going from 0 to 3. Let's put 3 over here. That makes this 1. Let's put this to be 2. Again, this is not drawn to scale. It's just to have an approximate idea. And if we plug in 0 into this function, we get 0 minus 2, which is -2. But since it's an absolute value, it becomes +2. So this is a height of +2. 1, 2, 3. So when x was 0, y was 2. That gives me this point here. If I plug in 1, so if my x is 1, 1 minus 2 is -1, and absolute value is +1. So we get this point here. If I plug in 2, 2 minus 2 is 0. Absolute value of 0 is 0. So we get the point 2, 0. And then lastly, if I plug in 3, we get 3 minus 1, which is 1. Absolute value of a positive value stays positive. So 3, 1. Okay, and we get this function here. We get the V. So again, it splits up into 2 regions. We have area 1, area 2. And now we could go find the total area by considering the area of each shape. And again, we're dealing with triangles. So let's go ahead and find it. So I'm going to do it in one shot. Area total, AT, is equal to A1 plus A2. Area 1 is base times height divided by 2, plus area 2 is also a triangle, so it's base times height divided by 2. And the base of the first triangle is a distance of 2, times the height, which is also a distance of 2, that divided by 2, plus the smaller triangle, area 2, the base is the distance from 2 to 3, so 3 minus 2, that's a distance of 1, times the height is also a height of 1 over 2. This gives us 2 times 2, which is 4, divided by 2 is 2, and 1 times 1 divided by 2 is a half, giving us 4 over 2 plus a half, which is equal to 5 over 2 units squared. And that's the total area for this region here. Okay, so we just integrated a function without integrating, just interpreting in terms of area, we found the area under the curve of this function here when we don't know the summation for absolute value functions. Okay, so this allowed us to solve absolute value functions by sketching out the graph. Okay, so we have constants, we have linear functions, we have absolute value functions, and now let's look at the fourth case. So in our fourth example over here, it says to evaluate in terms of area, do not integrate, do not anti-differentiate. We have to find the integral of -2 to 2 of square root of 4 minus x squared dx. So here we have a square root, so we cannot use our summation formulas here, or the Riemann sums, because we don't have the sum of a square root. So this is one where we're actually stuck. We can't solve. We have to evaluate in terms of area. Okay, so how do we sketch this function? What does this function look like? Well, consider the integrand. We have, this is f of x. Okay, so we could write f of x equals square root of 4 minus x squared. But f of x is just y. So y equals square root of 4 minus x squared. To get rid of the square root, we could square both sides. So here we're left with y squared equals 4 minus x squared, because the square root and the square cancel, leaving us with what's in the inside. And then bringing the x squared over, it becomes positive. We get x squared plus y squared equals 4. This should look familiar. And moreover, we could add this and replace 4 with 2 squared, right? Because 2 squared is 4. This should remind you of the equation of a circle. X squared plus y squared equals the radius squared. So here specifically, we're dealing with a circle of radius 2. So let's go ahead and draw that. So this is the y-axis, this is the x-axis. And we have a circle of radius 2. Our job is to find the area of a circle. -2, -2. Oh, sorry, +2. But wait, we're dealing with functions. This isn't a function. This fails the vertical line test. If I draw a straight line here, it cuts through 2 points. So this is no longer a function. Why are we allowed to consider the circle? Well, the question to that is that you can't. You can't deal with the entire circle. When you're dealing with this function, it has to pass the vertical line test, which means that we're either considering the top half of the circle of the or the bottom half of the circle, not both. So since it's positive in front of the square root, we're dealing with the top half of the circle. And we're going from -2 to 2 on the x-axis. So, oops. So -2 all the way to 2. So we're dealing with this region here. Okay. And how do we find the area of this region here? Well, we're going from -2 to 2, so we're just dealing with a semicircle. So we know that the area of a circle is equal to pi r squared. So what's the area of a semicircle? That's right, you just divide it by 2. So pi r squared divided by 2. So we want half the circle, so we're dividing our answer by 2. So let's go ahead and do that because we know what the radius is. The radius of the circle is 2. So we replace r with 2 divided by 2. This gives us 2 squared is 4 divided by 2 gives us 2 pi. And that's the area of the semicircle. 2 pi units squared. So this is a function which we cannot integrate or anti-differentiate by hand. We have to consider it in terms of area. Okay. But before I let you go, I have a question. How would you solve this if instead of -2 to 2, you went from 0 to 2? Think about that. What if this was a 0? What changes? Well, this is saying we're integrating from 0 to 2. So the thing that would change is you're dealing now with not a semicircle, you're dealing with a quarter of the circle. Because you're now going from 0 to 2 on the x-axis. From 0 to 2. You're integrating from 0 to 2. So here, instead of dividing your circle by 2, you would divide the area of the circle by 4 because you're dealing with just a quarter. Okay. So the answer here would actually be just pi in this case. Okay. So just to quickly recap, the first type of integrals we're dealing with are constant functions. So if we have a constant from a to b, then that's going to give us the area of a rectangle. So if you have a constant function, the area becomes a rectangle. 2, if you have a straight line, so any linear function, what you're dealing with is triangles, so you're going to find the area of a triangle. 3, if you have absolute value functions, then you're going to get the v, which is going to create two triangles depending on the shape. Even here, we could have multiple triangles, not just one. So if you have absolute values, you're also going to get triangles. Typically, you get two of them. So you add both triangles, and that gives you the total area. And finally, if you have square roots, specifically of the form the square root of a number minus x squared, then we're dealing with semicircles or quarter circles, depending on the bounds of integration. Okay, so we're dealing with semicircles. So these are the four new types of integrals that we could integrate without solving them using Riemann sums and just looking at their actual functions and finding the areas with formulas that we know. Okay, so let's combine everything and put all our knowledge together and answer this final most difficult question. So in this next example, it's separated into two parts. So the first part says to calculate the definite integral by interpreting them in terms of area. So the function that's given f of x is a piecewise function. So they tell us to use the absolute value function for absolute value of x plus 3 minus 8 on the interval from -8 to 0. And then on the interval from 0 to 4, we're going to use the square root of 16 minus x squared. Let's go ahead and find the area under the curve of this function here. So we're essentially looking for the integral from -8 to 4 of f of x dx. The best thing to do here is to deal with each term individually and make sure you're on their corresponding intervals, okay? So the first thing I'm looking at is the absolute value. So my absolute value, I'm going to rewrite this as the integral from -8 to 0 because the absolute value is being used on the interval from -8 to 0. So that's what my bounds of integrations are going to be, of 4 absolute value of x plus 3 dx. Plus, I left out this little piece. Why? Because I'm going to treat it like a constant. So now I'm going to integrate. It's actually a minus, so let me switch that to a minus right away. I'm going to integrate again from -8 to 0 of just the constant 8 dx. Okay? So again, the -8 is still on this interval. And then lastly, we have the square root function, which is on the interval from 0 to 4. So plus the integral from 0 to 4 of the square root function, 16 minus x squared dx. Okay, so we separated into three pieces. So this whole integral, we'll deal with each term individually. Let's start off with the first term. Okay, so the first thing I noticed from the first term is that it has a constant of 4. We haven't seen this yet, but you could still graph it with the 4, but just to make this easier, I'm going to take the 4 out. Is that going to make it easier? Yeah, it's going to make the numbers a bit easier to graph. So I'm going to pull the 4 out. It's a constant. This is a limit. The integral is a limit of sums, and we know that whenever we have a constant inside a limit or a sum, we could pull it out and put it in the front. So that's exactly what I'm doing here. So I'm putting the 4 in the front, and I'm just going to graph the function of the absolute value of x plus 3. So this one over here, let's sketch it. The absolute value function. This is 0. It's on the interval from -8 to 0, so we have -8 over here around. This would be -4. This would be -6. This would be -2. 1, 2, 3, 4, 5. The top here is 5. The scale on the y goes up by 1, so 1, 2, 3, 4, 5. And let's go ahead and sketch this. So if I plug in -8, I get +5, which is around here. If I plug in -6, it gives me 3, so it's around here. If I plug in -4, it gives me 1, around here. -3 would give me 0, so that hits over here. And then if I plug in -2, we get +1, so it comes back up. And then if I plug in 0, I get 3 up here. So we get this V like this. Okay. So we have our two regions, area 1, area 2. And let's go ahead and find the area of each. So let's do this in red. Area 1 is a triangle, so it's base times height divided by 2. The base of the triangle goes from -8 to -3. That's a distance of 5. So we have 5 times the height. From here it's 0 to the top here is 5. So 5 times 5 divided by 2, giving me 25 on 2. Area 2 is equal to, here it's from 3 to 0, so that's a distance of 3. So again, it's base times height divided by 2. Let's write our formula. The base is 3 and the height is 3. So this gives us 9 on 2 units squared. 25 on 2 units squared. So in total, this region here is equal to 4, because we still have the 4 that's sitting on the outside, times the area from -8 to 0 of this function, which gave us 25 on 2 plus 9 on 2. Adding the numerator, we get 25, 5, 34 on 2, which is 17. Okay. So that's this piece here. Let's erase and do the next piece. The next piece that we're dealing with is this region here. So let's erase this function, just to give myself some room. What do we have? Again, we're on the same interval from -8 to 0. And the constant's at 8. So it's not drawn to scale, but a constant we know is just a straight line, giving us a rectangle. So it's not drawn to scale, it actually ends up being a square because the distance of the base is 8 and the distance of the height is 8. So area of a rectangle, in this specific case it's a square, so it's going to be length times width, which is 8 times 8, which gives us 64 units squared. Okay, so over here we're going to have minus, so this is an equal sign. This answer minus 64. And now lastly we'll do the last part, the third region. So we did the first piece, we did the second piece, and we have the last piece over here. So the last piece, if we sketch it, it's on the interval from 0 to 4. And it's the square root of 16 minus x squared, so we know this becomes a circle of radius 4. But since we're on the interval from 0 to 4, it's just a quarter circle of radius 4. So the area of a quarter circle is pi r squared divided by 4, and we know that the radius is 4. So pi times 4 squared divided by 4, and 4 squared cancels with one of the 4s, so leaving us with 4 pi. So this is plus 4 pi. Okay. So we haven't integrated, we just interpreted all in terms of area, and now we're ready to solve. So 4 times 17, let me use a calculator. 4 times 17 minus 64. This gives us 4 plus 4 pi units squared. And that's our final answer. Okay. So I hope this helped. I hope you have a better understanding of solving definite integrals by interpreting them in terms of areas, and keep practicing. I'll see you in the next video.